I've always wanted to learn how the internet works under the hood. So in this series, I'm going to be building my own networking stack. I'm not going to reinvent the wheel or start from scratch. I'm going to build a simpler version of the real thing. The goal is to build a reliable, two-way byte stream that can facilitate communication between two computers over a network. The first milestone in this adventure is to build out the components that make up the Transmission Control Protocol, or TCP. TCP is responsible for making sure packets of data arrive at a destination with no data loss, and that the packets are placed in the correct order for consumption by the destination host. It's used extensively on the modern web, and the Transmission Control Protocol is arguably the most prevalent computer program in existence. I'll get started by familiarizing myself with existing tools built for reliable two-way communication over a network. One example is the Telnet program. I'll use it to connect to Stanford University's CS144 host server and send some bytes over the network and hopefully receive some bytes back. I've just opened a TCP connection to the server, which is now waiting patiently for me to send it some bytes. To communicate with the server, I'll send it a simple HTTP GET request. Let's see what the hello endpoint does. Success. The HTTP request succeeds and the server sends us back some bytes in the form of a nice little greeting. Next, I'll use the Netcat program to experiment with being on the other side of the connection. I'll pretend to be a web server and start listening for inbound TCP connections on port 9090. I'll leave Netcat running, and then in another terminal window, I'll connect to Netcat using Telnet. Now I can see that Netcat recognizes the connection, and I now have a reliable two-way byte stream between the two terminals. Any bytes I send from one side are consumed and outputted by the other side. If I terminate the Netcat program, it will terminate the TCP connection and the Telnet program will immediately quit as well. To avoid writing everything from scratch, I'm downloading a small educational codebase called Minnow. Built by Stanford University, Minnow is a C++ wrapper for some Unix system calls. These will come in handy for creating and using sockets. Let's see if Minnow compiles. Looks like the compiler isn't happy with this constexpr declaration. Let's see what happens when we remove it. Much better. My first warm-up task is to build the webget program, which is a simple function that creates a TCP socket, then connects to a web host and makes a simple GET request. Much like I did earlier with the Telnet program. I'm given a function signature getURL, which takes a hostname and a path as arguments. I'll need to use the TCP socket class and the address class, which act as simplified interfaces to the underlying socket library. So let's get familiar with the TCP socket and address classes. How should we do this? Well, looking at what classes they inherit from seems like a good place to start. The TCP socket class inherits from the socket class, which makes sense, but to be honest, I'm still confused on what a socket even is. Let's keep following the class hierarchy. Okay, now it's starting to make more sense. Socket inherits from the file descriptor class. A file descriptor is like a resource handle to a file or a file-like device, basically some segment of data that we can read from and write to. If we look at the public interfaces for these classes, it should give us a better idea of what tools we have available to build with. Our file descriptor class will give us a few useful tools, like being able to check whether we're at the end of file or whether our file descriptor has been closed. Back in the socket class, I can see some other useful public methods. The one that jumps out at me is the connect method, which takes an address and allows us to connect a socket to a specified peer address. This is definitely going to come in handy. Let's see what it does under the hood. Looks like it uses a POSIX system call to connect to a socket on another computer. It takes a socket address in the form of an IP address. But that raises a question. How do we get the IP address given we only have the host name and a path? Well, let's see what the address class can do for us. It looks like it's a wrapper for the sock address object, which is required by the underlying system call. But is there some function we can use to get an IP address given a host name? Yes, there's a constructor for exactly that purpose. It takes a host name and a service name. What's a service name? Let's check the implementation for more clues. So it looks like it's a string defined in the etc services file that maps to a port number. Obviously, HTTP is the port that we'll want to use, but now I'm curious, what's inside the etc services file? Looks like there's a few hundred common port numbers coupled with their protocol, each given their own unique name. And at the top of the file, it tells us who is responsible for naming these ports. The Internet Assigned Numbers Authority. Looks like they're a standards organization that oversees things like global IP address allocation, domain name systems, and a bunch of other internet protocol related numbers. That's pretty cool. Anyway, now that we know how to get an IP address given a host name, I think we can get started on this program. Firstly, I'll initialize the TCP socket object. Then I'll resolve the IP address of the host using the address constructor, giving it the host name and the service name. Next, I'll connect the socket to the host, establishing our two-way reliable byte stream. Now that the socket is connected, the host will be waiting for some kind of request, so I'll send it a basic GET request. Now, how do I actually send this through the socket? I forgot to look for a send function earlier. Of course, we want to write data to the socket. The socket is, after all, a file descriptor. Now we need to read the response packets from the host, and there could be many packets. So we'll need to keep reading until the socket reaches an end of file state. Let me guess, if there's a write function, there must be a read function. Perfect. I'll just print the response to standard output. And that should be good. Let's see if it compiles. Whoops, couple of mistakes. Forgot to specify which socket to connect to, and used the wrong quotation marks. Let's try again. Now it compiles. Let's give it a test. Beautiful, the request succeeded. Now that I've used reliable byte streams in my program, it's time to start building one myself. I'll begin with a basic in-memory byte stream. The complexities of implementing a reliable byte stream over a network will come later. The idea is pretty simple. I'll create a data structure that represents the stream, allowing me to write and read data efficiently. In this setup, the byte stream needs to have a capacity to limit its memory consumption at any given moment. This way, I can control how much data is being written and read, making sure that the stream doesn't become overloaded. To keep things simple for now, if the sender tries to send too many packets, the stream will drop the excess packets and they'll be lost. It'll be up to the sender and the receiver to manage the amount of data being input and output from the stream. The byte stream will also allow the sender to signal an end of file state, basically indicating that no more data will be sent. This way, the reader knows not to keep reading from an empty stream. If we look at the base code that Minnow gives us for this purpose, we can see that there's a few things missing. Firstly, we'll need a data structure to store the data inside the byte stream itself. I'm electing to use a queue of chars. This will provide constant time pushing and popping to the byte stream. Another option you could use is simply store your bytes inside a string, then concatenate the string and slice the string when needed. The problem with this is it won't provide constant time insertion into the byte stream. If you want to insert to the front of a string, you have to shift every other element in the string by one, making it a linear operation. Next, we'll need a way to store the end of file state of the stream. This can be done with a simple boolean. And for testing purposes, we'll also need to store the amount of bytes that have been pushed and the amount of bytes that have been popped from the stream. Inside the implementation file, I'll initialize those new data members. And then I'll start filling out some of the easier class methods. A lot of these are just getters and setters. Available capacity is just the total capacity minus the amount of bytes in the stream. IsFinished returns true if the stream is closed and there are no more bytes left in the stream. The peek method is interesting because it returns a string view, so my guess is that we need to return a string view to the front of the queue. Now the more difficult methods, push and pop. Push takes some data as a string. My first thought is, if the stream is closed, we don't want to push any more data. Next, I want to iterate through each character in the string and push it to the stream, but I don't want to go over the available capacity. So for every character, I'm going to check if we actually have capacity to push to the stream. And finally, we can't forget to do some bookkeeping. And finally, the pop method. Firstly, I want to prevent the reader from reading an empty stream. Then, since I'm given the len argument, I want to pop from the queue that many times. Okay, that looks good. Let's see if it compiles. Looks like I forgot to include the queue header file. This time for sure. Great. We've had a heap buffer overflow. Not good. So after some painful debugging, I've found the culprit. Inside the peek method, basically you can't return a string view to the front of a queue of chars. So that leaves me with two options. The first one is rewrite the entire data structure to use a string instead of a queue. That sounds annoying to do. Another option I have is to store the front of the queue on the byte stream object as a string. That will require a new data member, and I'll have to keep it in sync with the top of the queue anytime that I push and pop from the queue. So let's do that. Alright, let's try again. Yes, all tests are passing. I like knowing that my byte stream can get 350 million bits per second throughput. Well, thank you for watching part 1 of this series. Please feel free to leave a comment if you have any expertise in the networking field, or even if you just have any critiques. I'm always open to learning from others in this field. Thanks again for watching, and until next time.